Okay, so today we'll start with this muon decay calculation. Okay. So why this is important? Because we'll see while doing this thing. But before jumping into this calculation, let's try to understand what is the process that we want to look at. You have some muon having a momentum p, and that goes as electron with the momentum p prime, and then we have a anti-electron neutrino with k prime, and then you have a muon neutrino with some momentum k. Okay, so this is a process that we want to look at. Now, before the discovery of the Standard Model, okay, so how this process was computed using the 4 Fermi theory, okay, using this 4 Fermi theory, and it captures a lot of quantum field theory and the essence of Standard Model within it, but when it was proposed or computed, it was not realized like that. The reason is, if you look at in this particular process, there are 4 fermion fields are involved. 4 fermion fields, right? And each having mass dimension is 3/2. So now, if you look at this process, so this process you can think of like there's a muon and there's an electron, anti-electron neutrino and muon neutrino. So this is like a point vertex, right? This is mu, e, mu tilde, and mu. Yeah. So now, if we have to recast this kind of decay process, okay, in the form of this point like interactions, then you can see the operator or the term that you have to write down in the Lagrangian, okay, will have a mass dimension 3/2 times 4 equal to 6, right? So now we know that in 3 plus 1 dimension in quantum field theory, when we are writing each, so we are actually restricting ourselves to dimension 4 terms, because as we have mentioned and discussed earlier, that naively, if we look at the operators which have mass dimension more than 4, they will be accompanied by coupling which will be having mass dimension negative, and those are actually difficult to denormalize. I will not say impossible, but it's difficult to denormalize, right? And so in that context, if we have to write down this kind of 4 fermion field operator in the Lagrangian, which can describe this process, so that operator will have mass dimension 6. So certainly the coupling that will be associated with this operator will have mass dimension -2, such that we can accommodate this operator and the associated coupling in the Lagrangian density, which are having a mass dimension 4. Now let's see what kind of contact interactions we can write down such that we can describe this process, and that interaction looks like, so I'll explain all the variable. So you have a electron field, and then you have a 1 minus gamma phi, you have a 2 currents there, and then you have a mu gamma lambda 1 minus gamma phi psi mu. So these are basically these 4 quantum fields which are representing these particles. Okay, and now if you see what are these quantities, these are nothing but my current J lambda, and this is another current J lambda, right? So effectively, this Lagrangian you can think of as some couplings times the product of these 2 currents. Okay. So the question is basically here, now what is the mass dimension of this quantity? So mass dimension of this must be -2 such that this having an order dimension 6 can be cancelled, and as a whole you will get the full term of mass dimension 4. But now you can ask me, okay, that this coupling is a mass dimension 2 -2. So this is not the usual one that we talk about. You are perfectly correct. So what we can think of this GF, I do at this point we do not know what is GF, but it certainly looks like it is like some dimensionless coupling divided by some kind of mass square. This kind of, you know, um, functional dependence of mass, I would expect if GF should have a mass dimension -2. Now, what is this m square? So this is where one can think of that, okay, so it may happen that this is a connecting between this, the two currents are there. Okay. Now, these two currents may be possibly connected by a propagator. Okay. And this propagator is of some field whose mass is m square. And if it is so, then what would happen? Because you know that if it's a bosonic propagator, then it will have some kind of p square minus m square kind of dependence. And then if we go to a limit where m square is much greater than p square, then we can expand this propagator in this following form: 1 by m square, 1 minus p square by m square inverse. Right? So then the leading term, when the p is much small, I can ignore the p square by m square. So this will behave like a 1 by m square. And now if you calculate this kind of full diagram, then we will come to know what is the possible origin of this kind of thing. So in other words, we can think of that at some energy higher than the energy where you are performing or looking into this muon decay, the actual process looks like this. But because when you perform the experiment or look at the decay of this muon with a very low energy, that means the momentum transfer is very small. There, this one is approximated like this. Okay, and this is very important, because when you see that this is basically also can be described by the standard model, then in the standard model we have W boson, which is the gauge bosons, massive gauge bosons, and they lead to this kind of diagram. And when you expand the W propagator, you basically get this kind of effective terms, right? So that's why this process is very important and signifies a lot of things in the concept of quantum field theory. And also we'll see that when you calculate the decay process, actually, as we know, if you're working in a renormalizable theory, the cross-section that will compute that actually doesn't increase infinitely with the energy. Okay, if it is so, then it will violate the unitarity. And but if the theory is not renormalizable or it's not a renormalized theory, then the cross-section K can increase with the energy. It's a violation of the unitarity. Okay, and then you may think of that theory is not a complete theory or UV complete theory. It is rather an effective theory, and it is valued up to certain energy scale. So we cannot increase the energy infinitely. So that's how we can protect the unitarity up to certain energy. And that's how the first we'll see how to compute the decay width for this particular process, and then we'll argue that okay, at low energy this is a very good approximation, but once you make the energy of the experiment or the observation larger and larger, then there's a clear departure from the theoretical prediction and the experimental result. And that's where the failure of this theory to explain those kind of experiment data actually opens up the window of the new physics, and that new physics is nothing but we'll see will come out to be the standard model. So this will, the failure of this four Fermi theory at higher, little bit of higher energy actually paves the direction to modify this theory in the form of a more complete theory, and which is actually the standard model. So you can think of this theory as a seed of the standard model. Okay, yeah, up to any question? Okay, so now let's see how we can compute this thing, right? So this is the Lagrangian, as I mentioned, which will describe this process. Okay, so now the first thing we need to know that for, and we have seen already that for this kind of one going to 2, or here like one going to 3 body decay when is going on, then we could write down the decay width of this thing. So we can write down the decay width, or sometimes it's called the rate of muon as 1 by 2 mu. Then you have a dqp prime by twice per. So this is the phase space part. So now we have one going to 3 body. So we have a 3 body phase space. So all these 3 particles, we'll write down the phase space for them. So this is, for example, d4p prime, which you can write down in this particular form through the theta function integral. And then the 2k naught, and then dqk prime by twice pi cube twice k naught prime. So this is the 3 body phase space part. And here, instead of energy of the muon, we are replacing it by the mass of the muon, because we are working in a muon rest frame. So we are working in a muon rest frame. Okay, and that will not alter our any decision on that thing. So you can always go to the muon rest frame here. And then we have this momentum conservation, rather 4 momentum conservation. So you can see the momentum will be distributed into electron, muon neutrino, and anti-electron neutrino. So that is that P should be the equivalent to sum of the all these 4 momentums of these particles. And then we have a spin average and the spin sum over this amplitude square. Okay, so this is the mod m square. So first we need to see how we can calculate the amplitude. Now this is 3 body, so immediately we can write down the amplitude as the coupling, and then the now you can see this amplitude is basically very similar to what is given in the Lagrangian, right? So here only difference would be the fields are replaced by their wave functions, because they are asymptotic states, so they are replaced by the wave functions, and this will be exactly on the similar format. So why this is how we can relate this thing? So if you remember in the Lagrangian, when you have a lambda phi 4 theory, okay, so and then if I ask you to calculate the amplitude for scattering phi phi going to phi phi, right? And then the amplitude of that process would be actually lambda, right? So that's how we basically mimic this contact interaction. So when there's no propagator, if there's a propagator, we have to sandwich the propagator between the correct states. Okay, here's a contact interaction, so there is no propagator. So we write down the the amplitude here directly. So this is the P prime, and then you have a gamma lambda 1 minus gamma phi. Then you have a anti-electron neutrino, so that's why you have a wave function accordingly. So that is the V antiparticle wave function. So nu E with a function of K prime, and then you have a U bar nu mu, which is a function carries a momentum K information, and the gamma lambda 1 minus gamma phi, and U mu the momentum P. So we have written down the amplitude now, and now what we have to do, we have to calculate the sum over spin mod of Fi square, right? And so if we have to calculate this half sum over spin mod of Fi square, what it will give you? So when when you write down the spin sum, that's from the then that will be converted into the trace, right? So that's what we'll see. So now this quantity is basically half sum over spin, and then you write down the, so what is your mod Fi square? So this quantity you can think of this dagger and the Fi, right? So you have an Fi, and then you take a conjugate or the dagger transpose conjugate of MFI from there, and you will calculate that thing. So if I calculate that, how will write down? E bar P prime gamma lambda 1 minus gamma phi V mu E K prime. This is one part. The second part is U bar nu mu K gamma lambda 1 minus gamma phi U mu P is the M part. Now M dagger part is basically your UE, but P prime gamma lambda. Okay, we can change gamma lambda now because there's a different gamma are contracted. So let's write it down as a gamma rho, and then we have a 1 minus gamma 5, and then we have a V mu E K prime dagger, and then similarly we have a U bar mu K gamma rho 1 minus gamma 5 U mu P dagger. Okay. So now we'll use this different kind of completeness condition and so on, but you have already seen the sum of the spin U bar equal to P slash plus M mass of the particle. So here we have three kind of particles. You have electron, sorry, you have four kind of particles. You have electron, you have muon, you have anti-electron neutrino, and muon neutrino. Though nowadays we know that neutrinos have a tiny non-zero masses, but the kind of energy influx we have in this process, and also compared to the mass of the electron and muon, these neutrino masses are insignificantly small. So that's why we'll actually assume that neutrinos are massless. Okay, so this will be our assumption, and this will not actually give you something very absurd which we cannot match with the experiment. This is a good assumption actually. Okay, so now if we calculate that, so what we get? Mod M square average. If I calculate, okay, so there's another term which I forget to write down, which is basically your GF square by 4, the coupling term. Okay, sorry, GF square by 2 rather, sorry. It was GF by root 2. So we have this term. So that will be here in the mod M square, you have a GF by GF square by 2. So now when you write down this term, so GF square by 4, because there's a half here, and this quantity what I'm writing is basically this one, right? So I'm not writing sum and all those things explicitly. So this quantity is the mod M square average. That's why I put the bar here. Bar stands for the average here. So this will be GF square by 4. And now because from the completeness condition from the fermion field, so what you will do when you take the dagger, right? So when you take a dagger, so you see that V will come up as a dagger, okay? And that U bar dagger will give you some gamma 0. And that gamma 0 will pass through this gamma rho and gamma 5, and it will combine with the V dagger and will give you the V bar. And then this V and then the V bar will give you the notion of completeness condition. And similarly, because it's a spin sum, so what I can do, this U bar and U dagger, which will give you the U, okay? So that U will combine with this U bar and give another completeness condition about the spin of the electron. And that's how I can make them convert them in terms of trace. So eventually, for the electron part and the muon part, I can keep out these two trace terms here. So this will be P slash prime plus Me gamma lambda 1 minus gamma 5 P slash prime gamma rho 1 minus gamma 5. So see, the gamma rho and gamma 5 is there. So those terms are popping out here. So if you combine with them, and here I have assumed that neutrinos are massless, so with the K prime, which is the neutrino momentum, that is not accompanied by any mass of the neutrino, but the electron will have. Then another term, which is basically on the muon sector, is your K slash gamma lambda 1 minus gamma 5 P slash plus M mu gamma rho 1 minus gamma 5. So again, K was the momentum of the muon neutrino, right? So that's why this is not accompanied by any mass, because we have ignored their masses, but this muon certainly has the mass, and the rest of the gamma matrix and gamma 5 matrices are actually following them. Now we know that gamma 5 anti-commutes with this thing. So we know that gamma 5 and gamma mu, let's say, anti-commutes, right? Now, if you use this information, now we can further simplify our previous structures. For example, this one, gamma rho into 1 minus gamma 5, which we can write down as a, now when you write down this 1 minus gamma 5 will be passing through this K slash, okay? It will be anti-commuting, so we will put a sign like this, K slash 1 plus gamma 5, gamma rho 1 minus gamma 5. But next step, again when this 1 plus gamma 5 will pass through gamma rho, it will pick another minus sign. So eventually it will be gamma rho 1 minus gamma 5, 1 minus gamma 5. Now we know also this gamma 5 square is identity. So this can be reduced in this particular form, gamma rho 1 minus gamma 5. Okay. Yeah, up to this part, any question? Okay. So now we'll do the similar game for both the sectors. Okay. And if we do that, then we can write down this mod m square average as the gf square trace of p slash prime plus me into gamma lambda k slash prime gamma rho 1 minus gamma 5, and then trace of k slash gamma lambda p slash plus m mu, and then gamma rho 1 minus gamma 5. Okay, so the whole thing now reduced to in this particular form, and now you can see that the 2 is coming from both the sectors, so 2 and 2 4, that cancel basically the fourth term associated with this gf square by 4. That's why there is no 4 in the denominator. So we have these terms. Okay, so then if you now look at one of the trace, let's say trace of p slash prime plus me gamma lambda k slash prime gamma rho 1 minus gamma 5. Now if I expand that, what I'll get? I get basically p slash prime gamma lambda k prime gamma rho 1 minus gamma 5 plus me gamma lambda k slash prime gamma rho into 1 minus gamma 5. This I can decompose further. So gamma lambda k slash prime gamma rho minus p slash prime gamma lambda k prime gamma rho gamma 5 plus me gamma lambda k prime gamma rho minus ME, gamma lambda, K prime, gamma rho, gamma phi. Right? So now we have familiar relations for this. We know the value of this trace of gamma mu 1, gamma mu 2, gamma mu 3, gamma mu 4, right? We know their value. This trace we know how to compute. This formula we have discussed earlier. And then also you know the trace of gamma 5 with 4 gamma matrices will give you epsilon mu1, mu2, mu3, mu4 kind of term. But gamma 5 with odd number or less than 4 number of gamma matrices, that will be 0. Trace of odd number of gamma matrices is 0, right? So that's why these two terms will not contribute, okay? And that's why what we'll find out using this prescription, the mod m square average, is basically now 16 gf square into p prime lambda k prime rho plus p prime rho k prime lambda minus g lambda rho p prime dot k prime minus I epsilon lambda sigma rho tau p prime sigma k prime tau, and the second term will be similar to this. So this will be p lambda k rho plus p rho k lambda minus g lambda rho p dot k minus I epsilon lambda new row. Let me check. Yeah, so that I should better write it down in the other way around because these are all above indices. So yeah, so epsilon lambda sigma rho tau, and this is basically your sigma, this is your tau, and then similarly here we can write down, because all are denominator indices, so lambda nu rho eta k nu p eta. Okay, so we have all these terms. So now when you multiply, you'll see that there is no free index, and that's what we expect because this mod m square doesn't have any free index, so it should be a Lorentz scalar. Okay, so now if we contract them, what we'll find out, the 16 gf square into p prime lambda k prime rho plus p prime rho k prime lambda minus g lambda rho p prime dot k prime times p lambda k rho plus p rho k lambda minus g lambda rho p dot k, and this epsilon you can write down the product of that, so epsilon lambda sigma rho tau times epsilon lambda nu rho eta, and then p prime sigma k prime tau, and then the k nu p eta. Okay, and because the other cross term where epsilons are basically antisymmetric, so inside the trace, inside this thing, because the antisymmetric property, that will be 0, so they will not contribute. Okay, so this is basically the symmetric part and the antisymmetric part are contributing, and here we have these relations also, epsilon, let's say lambda sigma rho tau times epsilon lambda nu rho eta equal to minus 2 of g sigma nu g tau eta minus g tau nu g sigma eta. Okay, so if you use all this form, then eventually you will find out mod sigma square average is basically 64 gf square p dot k prime into k dot p prime. Okay, so this is the mod m square we have computed. So now we'll go back to the relation and that we have started with, and that is basically your definition of the gamma. So this part we have computed, the last part, and then we put it back in that formula and we'll see what further we can do. So then we can write down our form of gamma as gf square by pi to the power 5 mu, and then you have a phase space integrals. So d cube p prime by twice p naught prime, d cube k by twice k naught, and then you have a d cube k prime by twice k naught prime. You have a delta 4 p minus p prime minus k prime, and from this mod m square we have this p dot k prime and then k dot p prime. Okay, so this is the form that we have achieved. So now we have to perform this phase space integrals, and that's what we want to do. So then we assume the form of the gamma in this particular structure, let's say. So gf square by pi to the power 5 mu d cube p prime by twice p naught prime. Okay, and then we suppose that all other integrals, if we are done with that, then we'll be left with something like p lambda, p prime rho, and some unknown quantity which is lambda rho p minus p prime. So this is what we expect and to calculate, right? And now what is this I lambda rho p minus p prime? Okay, this is actually your d cube k by twice k naught, d cube k prime by twice k naught prime, and delta 4 q minus k prime, k lambda prime, k rho, while q equal to p minus p prime. So if you perform one of the integral, so you will see, so the rest of the part you are dumping in the I lambda rho. Now, as I said, so we can write down this measure in terms of d cube k by 2k prime, but eventually if you think that this is actually Lorentz invariant quantity, so we should keep in mind that whatever we are writing d cube p by twice e, or the zeroth component of the momentum, it's actually you can write down in terms of 4-dimensional measure and accompanied by the delta function. Okay, fine. So now, what is this I lambda rho? So this I lambda rho, it's a rank 2 tensor, right? Because it is a lambda and rho. So then, this form of the I lambda rho, if we have to write down in a suitable way that the coefficients are basically Lorentz scalar, then it can have only this possible form, q square g lambda rho plus b q lambda q rho. Okay, for any arbitrary vector, 4 vector, let's say q. So this is the possible way of we can decompose, rank 2 tensor, which has the correct transformation property under the Lorentz transformation, and the coefficients are Lorentz scalar. So here A and B, they are basically Lorentz invariant, or you can consider them as a Lorentz scalar. Okay, scalar in a sense of invariant. Okay. So then what you can see that you can write down these both the quantities, okay, from in terms of g lambda rho. So if you can calculate g lambda rho, and then if you do this kind of contraction, so what you will get, okay, g lambda, when you take, so it determines a 4 dimension, so you will get basically 4a, okay, plus b And now this is not a contrast of G, but Q lambda G rho G lambda rho, that will give you the Q lambda, which is the Q square. So whole Q square will come out. So I can write down this thing. And then we have the explicit form, the I lambda rho here. So that I can write it down as a d cube k by twice k naught, then d cube k prime by twice k naught prime, delta 4 q minus k prime, and then k prime dot k. Okay, yeah, so you can see if I multiply both and by the metric g lambda rho, I got k prime dot k. Okay, now similarly, if I contract this thing by q lambda q rho, so what I'm calculating now, g lambda rho, q lambda q rho. So what I'll get? So I get basically from the A term, because G lambda rho is there, so this will generate a Q square. So I get a Q to the power 4, and then Q lambda will be Q square. So this will be Q. So we'll get B times Q square and then another Q square. So this is the quantity I'll get. And on the right hand side, what I'll get is d cube k by twice k naught, d cube k prime by twice k naught prime, delta 4 q minus k prime. So q dot k prime times q dot k, because that will be contracted with k lambda prime and k rho. So that's how we get this thing. And this is, I can write down as a plus b q to the power 4. Okay. So now for neutrinos, my k square and k prime square equal to 0. Look at what is my k and k prime here. When you write down the amplitude, yeah, so k and k prime are the 4 momentum of the neutrinos. So, and we know that 4 momentum square is basically mass square. Okay, invariant mass square. So, but as we have said, we have started with the assumption that our neutrinos are massless without loss of any generality. So your k square and k prime square are equal to 0. And if we calculate, then k dot k prime in center of mass frame, okay, in CM frame. So what you'll get, you will write down k0 prime minus k vector prime. So is effectively, you can write down as a 2 k naught square. Okay, because remember your k plus k prime vector is basically 0. Okay, and your k0 is basically your mod of k because of the massless limit. So if you use this in functions, you find out this part. So now if we employ in this both this formula, so what we get for a plus b q square in the center of mass frame is actually your d cube k by twice k naught, 1 by twice k naught, delta q naught minus twice k naught square. Okay, and remember, so our in this particular case, right hand side, there is no angular dependence. So when you perform this volume integral d cube k, the angular part will give you theta integral and the pi integral. If you perform, you get basically 4 pi from that thing. Okay, so if you compute this, then what you resultant is basically 4a plus b is equal to pi by 4. Okay, and then similarly you perform the second integral, which is basically a plus b to the 4. From there you will generate, so this intermediate step I am giving as a homework, so you should practice this thing. These are the simple integral. Okay, so the same way you perform this integral with these considerations, that k square k prime square equal to 0 and k dot k prime in the center of mass frame. So these two quantities we finally got. Okay, and now if you solve them, what you find out, a and b, and after solving a and b, you put them back. So you know what is the tensor decompositions for now. So 2q lambda 0. So this part you exactly know now. And once you know this part, we plug it back in the gamma, which is gf square by 24 pi to the power 4 by m mu dq p prime by twice p naught prime p lambda p prime rho. So I lambda rho will contain this part q square g lambda rho plus twice q lambda q rho, and for the simplifications gives you g square by 24 pi to the power 4 m mu dq p prime by twice p naught prime q square p dot p prime plus twice p dot q p prime dot q. Okay, fine. So up to this part is fine. And now the formula that we have introduced in the gamma, so and the rest frame of muon. So if it is in the rest frame, so in the rest frame of muon, how can you write down the four momentum? It's basically m mu, and there is no three momentum, so this is the case, right? And this frame, if you write down the electron momentum, so you basically write down the p prime lambda is equal to e and then the p prime. So EE is not the PE because it associated has some kind of mass. So for the neutrinos case, the mode of three momentum is basically the energy, but because the mass, so three momentum mode and the energy will be different from each other. So now if you calculate P dot P prime, so it's like product of this four vector, what you get m mu EE, because three momentum will be multiplied by the zeroth component of the three momentum of muon, right? So this is for the electron and this is for the muon. So we get this quantity. So now we can calculate q square, which is p minus p prime square, which is p square plus p prime square minus 2p dot p prime. So p square will give you the invariant mass of the muon, so m mu square. P prime square will give you the electron mass square, and this we have already calculated. So this will be m mu times electron energy. And we have p dot q also, which is p square minus p dot p prime, which is m mu square minus m mu electron energy. We have p prime dot q, which is p dot q minus q square. So we get this quantity. So now you see all are basically written in terms of the physical quantities. So now if we perform and replace this four momentum product, so what you'll get gf square by 24 pi to the power 4 dq p prime by twice EE, and then we have all the invariant mass square plus m square minus twice m mu EE plus twice m mu minus EE m mu EE minus m square. Okay. So this part we have computed. So dq p prime, now we can write down in terms of, because p prime is the momentum of the electron, so we can recast this dq p prime in terms of electron energy. So and then perform the three momentum integral, so it will be written as gh square by twice 4 pi to the 4, so which is your d e, and then the mod p prime like this, and then we have this quantity. So I'm not writing this quantity again. So this one. Okay. So eventually we can say that we have been able to calculate this quantity d gamma by d e. Okay. So from there we can write down the differential dq with respect to the electron energy as gf square by 12 pi cube E square minus M square. Okay, and then we have a M mu square plus M square minus twice M mu EE times EE plus twice M mu minus EE M mu EE minus M square. Okay, so this is the the decay width of the muon of this quantity. So what does it say? That if the muon is decaying, then we'll observe the electron having the probability, having the energy between E and E plus dE, that is given by the probability of finding electron with energy between EE and EE plus DEE is 1 by gamma, weighted by gamma, E, E. Okay, so this is basically, that's how we can calculate the total and differential decay width. And this differential decay width is written now. If we, for example, further we perform the assumption that, okay, so this can be simplified further if we say that M mu, which is order of 106 MeV, and where Me is the order of 0.5 MeV. So that means M mu is much greater than the Me. If we take into this consideration, then we can ignore electron mass with respect to muon mass. And if we do that, then we can further give it a very compact and form in this way: gf squared M mu by 12 pi cube E square 3 M mu minus 4 EE. Okay, so this is how we can write and differential this thing. So then, if we want to calculate the total decay width, then this gamma we can calculate between 0 to M mu by 2, because the energy of the electron can be maximum M mu by 2. So then we are done the gf square M mu by 12 pi cube E square 3 M mu minus 4 E, and then the dE. Okay, and this is nothing but the gf square M mu to the power 5 by 192 pi cube. Okay, so this is the total decay width of this thing. And now if you want to calculate the lifetime, okay, of muon in its rest mass, lifetime of mu in its rest frame is tau mu equal to 1 by gamma. So that is the total decay width. Okay, so that's how you can calculate the total decay width for any kind of decay process, whether it's 1 going to 2 or 1 going to n, whatever. But simply you can calculate the decay width for this thing. Yeah. So let's go back to the first slide where we wrote down this thing. Here, yeah. Now you see that basically we have muon is decaying to 3 body process. Okay, so now you can calculate the similar method to, for example, let's have a one particle is decay to n number of particles. So how the things will change? So then if there's n number of decaying products, then we will have n number of phase space. Similarly, we have one momentum conservation, and this will be like a p minus all n number of momentums will be there, and then the mod m square for that process. So if we calculate this step by step, we should be able to calculate any decay width starting from this. And if the particle is massive, then we can go back to its rest frame, and that will be much more simpler to calculate. And then because this is we are calculating the Lorentz invariant, so it would not matter whether we are working in rest frame or some other frame, because it is not a frame independent result, it's a frame independent result. Okay. Yeah, up to this part, any question?
So I have a naive question to ask. So in any literature, the experiment is done in the lab frame. So if we'll calculate the decay width in center of mass frame, then it should be equal to the experimental result. That means in the lab frame, because it's a low range invariant quantity, as you said. So
Yeah.
I will calculate that in center of mass frame, my result should be same. Is
Okay.
it so?
So the thing is basically the two things. One is basically the lab frame. When you calculate, that basically goes for the scattering, not for the decay. Okay.
Yes, sir. For example, if the decay process is for Z boson,
Yes.
then for that, I'm only talking about the decay process, not scattering. So
Yes.
Z is going, let's say, to any fermion, dileptons, let's say.
FF bar. Let's say fermion, anti-fermion, FF bar.
Yes, sir. Yes.
Yes. So the thing is basically, so as long as it's a massive particle, that's what I'm saying, that if the decaying particle is a massive particle, you can always go to its rest frame. Okay, and that should not alter your result. Now the thing is basically what happening, that's what I'm saying, look at my last comment that I've written down, lifetime of the decay width in its rest frame. Okay, so now as we know, if we can give some kind of boost to this particle, right? So if we boost them, then of course its lifetime and all those things will change. But what I'm saying, in the intermediate calculation for this particular, if I choose the moment, this is the rest frame, and then intermediately my assignment of the momentum comes, connected with connected with that particular choice, that should not alter my final result actually. But if you go to a boost this particle, okay, then of course we know the time dilation and all those things happens, right?
Yes.
So when we quote, so that's why when we quote any kind of decay width, for example, there's a PDG and all those books are there where the fundamental decay width and all those things are there. Okay, they are not the boosted one. They are basically computed in basically rest frame actually.
Okay, sir. Thank you, sir.
Yeah. Any other question? Okay, so this was a little bit long calculation, but this is very important calculation. As you can see that this gamma, when you calculate, and if you write down in terms of the momentum in the intermediate step, you will find out that this with the electron energy, okay, so then this decay with the amplitude actually basically increasing. Okay, but that should not be actually. It should be, if you calculate the scattering amplitude for this process, it should not increase with the energy. It should first increase and then decrease, which is basically that giving the unitarity. Okay, so this process will recompute. Okay, we will recompute when we talk about the standard model, and then we'll see that again after the standard model computation, if we say my propagator, that will be the W boson there, that if the W boson mass is very, very heavy compared to this electron and muon masses and other particle masses involved in this process, then we can perform an expansion of the W boson mass, and from there we'll see in that approximation that will exactly fall into this result. So that we'll see. And not only that, one of the important thing we can do, which is called the matching, is very important in quantum field and particle physics, that this is a low energy theory. So 4 Fermi theory is a low energy theory, and at this point you see, if we can experimentally measure the muon mass and the decay width of muon, then we can calculate the value of the GF, right? And if we can calculate the value of the GF, so what we'll find out, it's approximately this kind of values, 10 to the minus 5, GeV to the minus 2. Okay, but at this point, this is just a parameter. But later, when we do from the standard model, there we'll see, okay, so let me call it a matching with standard model, then we'll see that this GF square is basically some constant times some G square by MW square. Then experimentally, if we can measure MW and the SU2 gauge coupling for the W boson, associated W boson, and we put their values and the constant term, that value achieved through this matching is very much equal to this one. So that's a consistency we take, that this theory, Fermi theory, is we do not consider now as an independent one, but this you can think of as a low energy limit of the some standard model prescription. So these informations are embedded within the standard model. And that's how in particle physics, the new theories at higher energies are actually proposed. For example, when you talk about the standard model, and now we look for the beyond standard model. So what is the primary thing we have to see, that how we can embed this known theory into the unknown theory. Because if we get the unknown theory, okay, then and suitable energy limit if we perform, then we should get back the low energy theory. So that's how, these two different theories are connected with each other. Okay, is that one clear?
Yes, sir.
Okay. So so this is as of now as a low energy theory, we computed this, but from the standard model we'll recompute this process and we'll do the matching. Okay, fine. So this is the field theory, important field theory calculation before going into the Haber scattering and molar scattering that we'll do next week. But before that, I wanted to give you a different taste of this field theory, which is related more with the symmetry breaking and the group theory information that we have learned. So this is the one of the field theory calculation, and now let's do a slightly different thing. So let me introduce something called the symmetry breaking. Okay. So from the name, it is clear that when I call the symmetry breaking, that means there is symmetry, and then the symmetry is broken. Now the question is basically how we can break the symmetry. Okay, so there are two ways you can think of. One is basically in the Lagrangian, you start with saying that this is my symmetry, and then for example, let's say one of the important symmetry that is there is the gauge symmetry. Okay, so which protects basically, if you remember the gauge transformation, when you do under that gauge transformation, if you write down any term in the Lagrangian in the form of a binary in gauge field mu, this term is not protected by the gauge symmetry. That means this term violates the gauge symmetry, and gauge symmetry is a very fundamental symmetry. Renormalizability of the theory and many other properties are basically depend on that. So we cannot just break that symmetry by introducing this kind of term. So when we have this introducing this kind of non-invariant term in the Lagrangian, we call the breaking of those symmetries are explicit. So we can break some symmetries which are not that sacred explicitly, but certainly not the gauge symmetries. Okay, so then gauge symmetry, what are they doing? They are not allowing us to write down any kind of term which is bilinear in gauge fields, right? So then if it is so, how we can explain the massive gauge bosons? Because that is needed. We have observed that, and also there is a intermediate vector boson theory where we have massive gauge fields. If you see the Proca-Lagrangian, there's a massive gauge fields are there, but these gauge fields, gauge boson masses are not protected by the gauge symmetry. Now, to do in a very careful way, what we can do, we can introduce some new method of symmetry breaking, which is called the spontaneous symmetry breaking. Okay, spontaneous symmetry breaking or SSB. Now, what is the difference between the spontaneous symmetry breaking and the explicit breaking? The explicit breaking breaks the symmetry at the level of Lagrangian. That means Lagrangian is no more symmetry. But spontaneous symmetry breaking is an interesting tool which gives you a handle to break the symmetry spontaneously, not in the Lagrangian, but in the solutions. And what are those solutions of the here? They are the vacuum manifold or the vacuum configuration of the scalar field. So that means we have to design, our scalar potential in such a way that without adding an explicit symmetry breaking term, it automatically leads to some kind of symmetry breaking that will reach out to some point where our, the Lagrangians still respect the symmetry, but not the solutions. Okay, so we will not disturb the symmetry of the Lagrangian. Okay, but still we can generate the mass term of the gauge bosons. So that's why this is the most known suitable method to generate the masses for the gauge boson, and that's why we need to learn to understand the mass generation of the massive gauge bosons in the spontaneous symmetry breaking. Okay. So now, why this is spontaneous? As I told you, that when, okay, so let me give an example, then you'll understand why this is. So for example, let's say there's a potential of this particular form. Okay, so what kind of potential is this? You can write in scalar field, let's say m square phi square plus lambda phi 4. Where did m square greater than 0, lambda greater than 0? If it is so, then what we can see that at phi equal to 0, there's a minima, and if it is here, the particle is here, it will be there forever, right? But let's say I create a situation where m square is less than 0 and lambda greater than 0. Then my potential will look like, my writing is very, then my potential will look like this, okay? And then this is my v phi, this is my phi. Now you see, and why it is so? Because so this is not more anymore 0. So your 0 is basically here. So this is your v phi equal to 0. So then v phi equal to 0 is not the global minima. Here v phi equal to 0 is actually the local minima of the potential. So if you see at phi equal to 0, the v phi is 0. But now when phi is increasing, because your first term phi square and the next term is phi 4. So as long as phi square is dominating over the phi 4, so it will be decreasing because m square is less than 0. So that's why it is falling. Now at some point phi 4 will dominate over phi square, and then actually it will start increasing, and that's why it is increasing right now. So in these particular circumstances, when you have by the choice of the potential parameters, you can see the potential shape is becoming like a Mexican hat kind of potential. Okay, and then to start with, the particle at phi equal to 0 is basically here. Earlier it was in minima, and that minima was the global minima, but now it is here. Now, without any kind of provocation, this may roll down to this. For example, let's say if there's a discrete symmetry, phi going to minus phi, that tells you either you have two minima solutions, which is plus, let's say, phi c, and this is minus phi c. So now, when the particle is here, without any kind of provocation, it can go either this direction or this direction, right? So both are equipoable. So now, when both are equipoable, but out of this all equipoable probability, it will choose only one of them. And remember, this choice is not biased by any kind of, external reagent. That's why this is called the spontaneous symmetry breaking. Okay, so this point now, why is this symmetry breaking? Because when this is in particular solution is here, it can feel all the symmetry around it itself. But when the particle reaches here, then it cannot go and like this way. This is not allowed. Why? Because if it has to go, then it has to tunnel through this potential. And if you calculate the tunneling amplitude, then you will see that this tunneling amplitude is basically 0 because it to the proportion to the minus some constant quantity of the volume integral. And in the context of quantum field theory, you talk about the volume of the whole universe. So that volume is so large that it to the power minus of that volume is effectively 0. That's why the transition amplitude is 0. So it is trapped forever there. Now it cannot reach out this solution. That's why we call that this solution is no more there when the particle reach here. And that's why from the reference frame of this particle, the symmetry is broken. But you see, through this process, the shape of the potential remain unchanged. And that tells you the symmetry in the Lagrangian is still there. So that's why this is called the spontaneous symmetry breaking through the scalar field. Okay. Yeah. Up to this part, any question? Okay. So now, when there is a spontaneous symmetry breaking, what does it mean? So when it reaches this part, what does it mean? That means this field, when it is there, it has a expectation value which is 0. But now, when it reaches here, this quantity is nothing but the expectation value of this field. So the expression value of this field is non-zero, and that's what the symmetry breaking is done, spontaneous symmetry breaking. And the expression value of this field, what we call the vacuum expectation value, because this is computed in the vacuum. Vacuum is the ground state. So this is why you are computing this thing. So that's why you call the vacuum expectation value, and that's you call VEV. Okay. So now, if there's a non-zero vacuum value, and let's call this phi vacuum value is some kind of V. Now let's see what happens when I have a simple case. I have a scalar field and there's a gauge theory. So as you know, let's say you call a gauge theory is U1. So e to the power I theta phi, this is the transformation, and phi dagger is transforming it to the minus I theta phi. Okay, but here to make it a gauge theory, so what we have to do? We have to do theta is a function of space time. Then your Lagrangian is basically how to write down d mu phi dagger d mu phi minus m square phi dagger phi minus lambda phi dagger phi whole square. Okay, with your m square less than 0 and lambda greater than 0. This is the choice. Now, when in the vacuum expression, when the vacuum expression is phi, then what you do? You replace this phi by its vacuum value. This is the classical field theory we are doing. There is no quantum fluxes and so on. But if you do that, then what is your d mu phi? Your d mu phi is del mu plus I. Let me call it a G prime. Okay, a mu. So a mu is the E1 gauge field and phi, right? So now when I expand this term d mu phi dagger d mu phi, so one of the term that I'll get in this particular form Ig prime a mu phi and then minus Ig prime a mu phi. Oh yeah, phi dagger, right? Yeah. Okay. So this is the term we basically get. And now when they are getting a vacuum value, so basically what I'm getting, it is proportional to G prime square, this phi dagger phi phi, and then there's a mu. What is this quantity? This is the v square. So I get a g prime square v square mu. Now you see, I can generate a binary term in the gauge field, okay? But I have not broken the gauge symmetry of the Lagrangian. Only the vacuum configuration of the scalar field, they do not respect the symmetry, but that is fine. There's nothing harmful, okay? But at the cost of that, now I generate some quantity like this. So then I can say the ms square is basically g prime square, this square. Okay, so let me call the half of this. So yeah, so I should not say, yeah. So now V is a vacuum expression of the scalar field, so it has a mass dimension 1. So V square has a mass dimension 2. So this is perfectly the mass term of the gauge field. But importantly, the mass term of the gauge field depends on the vacuum expression value times the gauge coupling. The coupling between here, the scalar field and the gauge field. Now you see, if I go back to very previous case where the scalar field is not getting the vacuum value, that V is 0, the gauge fields are again massless, and then I regain the gauge symmetry in the vacuum configuration. But without this way, without spoiling the gauge symmetry of the Lagrangian, I can generate the mass term for the gauge bosons, and that's why through the spontaneous symmetry king, I can generate successfully the mass term for the gauge bosons without violating the gauge invariance of the theory. So that's why these are so important. Okay? Yeah, up to this part, any question? Okay. Okay. So now, what are the properties of this while doing this symmetry breaking? What we have to be careful about? Let's say I am now, this is the simplest case U1 I was talking about, but we have to understand this thing for the standard model. So let's try to generalize this thing. So now, if we start with, for example, let's say, some symmetry group G, which I have gauged, and then after the symmetry breaking, I want to get my G1 and G2 to be invariant, or let's say further I want to get this one, that if I start with G1 cross G2, then I want to break that symmetry to G3. Then how do I choose the vacuum expression value? That will tell you that whether I can go from this to this, or this symmetry will be completely broken. There is no remnant symmetry. Okay. So that is basically depends on the choice of the scalar field. So as you know, when you perform the symmetry breaking, one of the property of the spontaneous symmetry breaking is that all the quantum numbers, okay, all the quantum numbers associated with the scalar field, which is getting this vacuum expression value, are spontaneously broken. Okay. For example, if I have a scalar field which is basically charged, and that charged scalar field gets a vacuum value, then the charge symmetry or the electromagnetic symmetry will be spontaneously broken. And if the spontaneous electromagnetic symmetry is spontaneously broken, that will generate the mass term for the photon. But we know that photons are massless. So we should not use charge scalar to break that field. So that's why when I choose any scalar field, the representations under this G1 and G2 are, let's say, R1 and R2. That means if I have to choose the R1 is the representations corresponding to G1 and R2 is corresponding to G2. Or maybe I can make it much simpler. Let's say I have a SU2L cross U1Y, which is broken into E1 electromagnetism. Now, I need a scalar field which is not singlet under SU2L. That means it has non-trivial SU2 charges, because if it doesn't have non-trivial SU2 charges, I cannot break SU2. So first I have to identify which symmetry I want to break, and my scalar field must have that quantum number. Then only that will be broken. So SU12 quantum number must be there in the scalar field. And what is the lowest dimensional representation of the scalar? I mean SU2, that's two-dimensional. So I start with a two-dimensional scalar field. Similarly, if I have to break hypercharge symmetry also, then that field must have some hypercharge. Okay? Otherwise, the hypercharge symmetry remains unbroken. But at the end of the day, the field that I will get, components of the vacuum value, its electromagnetic charge must be 0. If electromagnetic charge is non-zero, then photon will be massive because E1 electromagnetism will be broken. So I want this, I impose these conditions to have a successful symmetry breaking like this. That I have started with SU12 and E1 hypercharge, and that is broken to E1 electromagnetism. So now you see, so if it is a SU2 doublet, then my phi will look like phi1 and phi2. So what is the isospin quantum number T3? It's a half, and this one is minus half. Now you see, any one of the component should have a signature of Q generated to be 0. And we know this is the relation Q equal to T3 plus Y by 2. So then, if I have to assign the hypercharge of these two fields, okay, I can assign only one, and that is basically half and half. And then, sorry, 1 and 1, because I'm using a different normalization. So it's 1 and 1. If it is so, then the phi 2, Q of phi 2 is basically 0. So then the expression value of phi is equivalently, I can write down 0 and phi 2 expression value. And this will break my SU12 symmetry and E1 symmetry, and it will lead to E1 electromagnetism unbroken. Now, in the process of unbroken, how do I know that how many gauge bosons will be massive, how many gauge bosons are massless? This we can do from the counting of the generators. So, to start with, you have SU2, which has 3 generators. For E1Y, you have 1 generator. So, total, I have 4 generators. And now, as an unbroken, you have E1 electromagnetism, which you have 1 generator, so 1 generator. So you can call number of broken generators equal to, you start with 4, you leave 1 unbroken, so 4 minus 1 equal to 3. And that's how you get 3 generators will be broken. And the number of broken generators is equal to number of massive gauge bosons. And now you go back and then see in the standard model, because you perform this symmetry breaking, you generate W plus, W minus, and Z, 3 massive gauge bosons, and 1 unbroken, so 1 photon. So that's how you count. Okay, so this is how basically we introduce the spontaneous symmetry breaking in our theory. Okay, but yeah, and then this is so far when we talk about the symmetry breaking the vacuum value, this is still in the classical level. So after that, what we'll do, we'll consider this theory to be the quantum. And as you know, once we into the quantum theory, then we cannot say this particle is trapped here and then sitting there. This will start fluctuating like this. Okay, this will have a small oscillations. And these oscillations will generate the fluctuations, and those fluctuations are the quantum fluctuations. Okay, and these quantum fluctuations, when they do, that means we have to perform, then we have to write down our V. So earlier this was V, but now after the vacuum expansion value and its fluctuations, so this will write down this way. So these are the fluctuations over the classical background, which is a constant term. This doesn't have a space-time dependency, it's a constant term. And then this phi scalar field after the symmetry breaking, it will take the form as a fluctuations over the constant background. The background is the vacuum expression value, and the fluctuations we call is the physical particle. And this is the physical Higgs boson will come up from there, and that will tell you how in the quantum field theory you perform the spontaneous symmetry breaking and how a fundamental scalar appear as a real field and the real particle. That we'll discuss in detail, but this is just to give you a different test than the calculation previous we have done, and this is just to paving the direction towards the standard model. And one important part is spontaneous symmetry. Okay. So this is just to give you the flavor of symmetry breaking, but don't worry, we'll do this thing in much more detail in the counter standard model, looking the whole spectrum with the covariant data and so on in the consistent way. But this is just to give you a flavor what actually spontaneous symmetry means and why it is important in the counter standard model. Okay, so I think today we'll stop here. So if you have any question.